All right, here is a key theorem for when we talk about sets and bases for our vector spaces. So the spanning set theorem says that if S is a set of vectors in a vector space and H is a span of those vectors, then one of the vectors is a linear combination of the remaining vectors, or if, okay, then the set formed by S by removing that vector still spans H. That has to be true because whatever that vector is a linear combination of the other ones. So if you just took that out, the vectors would still be a linear combination, okay? And H can't be equal to just the empty set for some subspace S, if that's a basis for H. So you can't just have the zero vectors in there and be like, done, okay, is basically what this means. So let's look at an example. Note that we have V1, V2, V3, and V3 is a linear combination. 5V1 plus 3V2 will get you V3. So if we have that H is the span of that, and you can see there's like a visual here of what that means. Well, we can get to V3 by taking 5V1 and adding 3V2. So you can see that graphically. Show that a span of V1 to V2, V3 is still just the span V1, V2. Well, that's because V3 is equal to this vector set. So span of this, span of V1, V2, V3 is some linear combination but V3 is just V1 and V2. So you could plug that in if you wanted to be really specific about showing this. But then these just get absorbed into here, these just get absorbed into here. And so you could say maybe different than C, that this is like D1 V1 plus D2 V2, which is then a span of V1 V2, okay? Now the second spot here is that is this a basis for the subspace H? So, or find a basis for the subspace of H. Well, we need the basis to be linearly independent, so we're not going to include vector V since that is a linear dependent. So basically, H just has to be the span of V1 and V2 because that's what's going to end up giving us that entire plane. It's just the span of V1 and V2. So the span of V1 and V2 must be the basis of H because it needs to be that linear set that spans the linear transformation, excuse me, of the set of vectors that span H is going to give us our basis. All right, here are two theorems. The pivot columns of matrix A are going to form a basis of the column space of A. And if two matrices A and B are row equivalent, then their row spaces have to be the exact same. So if they are row equivalent, their row spaces are the same, pivot columns of a matrix A form the basis of the column space of A. Let's go ahead and look at some examples for this. So form a basis for the column space of B where B is equal to these set of B vectors. And of those B vectors, let's find the pivot columns. So my pivot columns are here, here, and here. Therefore, I need to find, let's go back up to that definition, the pivot columns of matrix A form a basis for that column space of A. So that means that our basis must end up being B1, B3, and B5. Because you can find any of the other columns based on a linear combination of B1, B3, and B5. Okay, we should actually call this the column space of B. That's hard because it's also the basis, but it's the best way. So if you say, I'm going to go back here. We're actually going to call this S, okay, because this is going to end up being our span, okay? And so S forms a basis for the column space of B, because any linear combination of B1, B3, and B5, so all the pieces of S are linear combinations for all the column space of B. So B1, B3, B5 forms that basis. That's a better way to say this, okay? All right, let's look at this example here. So here I have matrix A, A1 through A5. It is row equivalent to matrix B above, okay, row equivalent. And the reason why, let's go back up to that theorem. They're row equivalent if their row spaces are the same, okay? If B is in echelon form, here we go, the non-zero rows of B form a basis for the row space of A, as well as that for B. So the basis of the row space of B would be based on the non-zero rows of B. And we can end up saying that these two are row equivalent. It's given here in the problem that they are row equivalent. So if I were to reduce this, I would get something very similar to B. Let's write down what that means. We know that means A, which is this matrix here, must row reduce to B. And just to remind you, so we don't have to scroll it back up, B is 1, 4, 0, 2, 0, 0, 0, 1, negative 1, 0. 0, 0, 0, 0, 1, and then all zeros here. Therefore, the basis for column A has to be the exact same columns as for column B. So that basis must be the span of A1, A3, and A5. Also, a basis for the row space must be row 1, row 2, and I ran out of room here, so let me slide this down. Row 3, like so.